Hello. Hi, everyone. We're going to start with uniform material today. We're going to go ahead and do approximating areas. The gimmick with this is that we have just kind of covered antiderivatives, which we will later refer to as integration. And this integration idea will help us with these sort of approximation of areas of functions, or not functions, of shapes of different curvatures that simulate functions. So, for example, we will be using rectangles to approximate the area underneath the function. This is the foundation of what we now call integration. To approximate the area under f of x uh, from a to b using n triangles. Step 1, divide the segment a to b into n subintervals of equal width. This will be noted as delta x, or the change of x, and you'll just plug in the pieces of this fraction. Then pick a sample point xi in each subinterval. This could be either the left or the right endpoints. You may not know what this is just yet, but this will be better visualized here. Let me just get through these steps. Okay. Then you'll compute the height of the rectangle by plugging in the sample point into the function of f of x, or f of xi. Then you simply calculate the area of the rectangle. Recall that the area is height times width, but in this case the height is our y value, which is f of xi, and then times that change of x, because that will be, and technically you could argue that this will be, the difference between xi and then the previous point, but it's going to be the same width no matter what. So this is just the better format versus this. And then you add up all the areas. So the idea of using the left endpoint and the right endpoint have different techniques, though they're both valid in their own merit. Um, let's go ahead and consider the idea of drawing four rectangles to approximate this area from 0 to 8. So if we're doing four rectangles, that means that we're going to split this up into four pieces. So 1, 2, 3, and yeah, 4. Okay, right here. If we're using the left endpoint, then that means we're drawing from the left here all the way across and making this little rectangle. Then at 2, we pick up that point here, draw that rectangle there as well. Then at 4, we pick that point, draw that rectangle. And then at 6, we pick that point and draw that rectangle. Using the right endpoints, using the same breaks as we did before, is picking from 2 the point that it touches and then drawing a triangle where it's the right top corner. For 4, it's the same thing. For 6, and then instead of using 0, like we did before, we're going to use 8. That's the idea of approximating the areas and simply doing this, height times width, point. Let's increase the difficulty of this example just a little bit, and let's say we're gonna do 8 rectangles. So we're to do 8 rectangles. Well, this should be easy to cut into, this segment should be easy to cut into 8 parts. We will use just all the whole numbers. We'll use 1, 2, 3, 4, 5, 6, 7, and 8. Same thing over here. Using the left as an endpoint, we'll start with 0 and draw the rectangle stopping at 1. Then at 1, 2, 2, 3, 3, and you can see this pattern keeps repeating. Let me just go ahead and finish this visualization. Okay. Oh, and then over here. So from the right, here, Now, the analytical way of getting these is shown below, where each xi is your starting point A, and then plus each iteration of the change of x, the equal width of x that you'll be using. Again, this is all dependent on how many rectangles you're doing with the approximation. But because I'm still drawing it, I still haven't actually told you what's the difference between the right endpoint and the left endpoint. Now, the difference is better seen. It was seen, okay, it was seen visually before. It's not better seen now, but it is just better stated now. The gimmick here is that notice these bits of area under the curve that is not captured. Well, we know that technically speaking, this is missing information, and the rectangle only caught so much of this information. So this is underestimation, where we are not taking the full area and we're under measuring it. Over here, you see a bit of an opposite effect. The opposite effect is that we are taking too much rectangle and we actually are capturing more noise than what's under the curve. So this is an overestimation. Now, at the end of the day, the more rectangles you get, the smaller these unders and overs become, but that's going to get mainly touched in day 2 of our lectures, of our week 4 lectures. So let's just use this material, okay? So example 1 reads, estimate the area under f of x, where f of x is equal to 2x squared minus x on the interval 1 to 3, using 4 rectangles and left endpoints. Then compare that to the area using the right endpoints. Okay, well, let's just do the change first because that's going to be the same no matter what. If the end point is, or the ending point is 3 and the starting point is 1, we need 4 rectangles. We're going to do the fraction 3 minus 1 over 4. That's going to be 2 over 4. It's going to be 0.5. So that means we're going to be taking breaks of 0.5. Let's go ahead and do this one by one. So we need first our initial point when I is equal to 1. So that's going to be x0 is equal to a, which is 1 plus I minus 1. So 1 minus 1 times the change, 0.5, which is just going to be equal to 1, since that comes out to 0. Then for the second point, we have it be x1, which is equal to 1 plus 2 minus 1 times that 0.5. That just comes out to 1. So we left with 1.5. And you could see this pattern pretty straightforward after this. 1 plus 3 minus 1, 0.5, so that's going to be 2. And last one, 4. That's going to be 2.5. So we have the left endpoints here. We have it at 1. We have it at 1.5, 2, 2.5. Now remember, at the end of the day, that's the location. What we technically need is the actual height. Well, remember, the height is measured as f of x. So we need to type this all in. We need to plug this all in for f of x. So let's go ahead and start. I have f of x0, which is just going to be 1, f of 1, and we have 2 times 1 squared minus a 1, so it's going to be just a 1. And I have f of x1, which is just f of, we said 1.5, Yeah, so that's going to be ugly. We can still definitely do it. We got 2 times 1.5 squared minus 1.5. We can do it out loud. I want to say this has become 1 point. Let's see. Fine, I'll just get out my calculator. Let's see. 1.5 times 1.5 times 2. So that becomes 4.5 minus 1.5, which is just 3. Okay, and we're going to keep going for all these points. Of course, 2. 2 times 2 squared minus 2. That's supposed to be 8 minus 2, which is just 6. And then f of x to the power of 3. F of 2.5. That's going to be 2 times 2.5 squared. Excuse me, I forgot to write that. Minus 2.5. That, again, I am just going to type in the calculator. 2.5 times 2.5 times 2. And then minus 2.5. So that's just a 10. So we see that for all of these, well, exactly 4 entries, we're going to use this notation. We have f of xo times that change, which is 0.5, plus f of x1 times 0.5, f of x2 times 0.5, and then f of 3 times 0.5. And we have 1 times 0.5 plus 3 times 0.5 plus 6 times 0.5 and then plus 10 times 0.5. For here, I'm not even going to worry about doing it all individually. I'm just going to type it into one big problem on a calculator to make my life just a bit easier. And then 10 times 0.5. Okay, so I got 10. And hopefully you all are getting 10 as well. So that's the gimmick here, right? Where really what they want is they want us to draw, okay, at what point is our function touching at the left endpoint? Alright, let's go ahead and now use the right endpoint. So over here, you're going to follow a similar idea where everything is just I is equal to 1, I is equal to 2, I is equal to 3, I is equal to 4. You stop at 4 because we're only using 4 right triangles. So let's go ahead and get out these values. Let's plug it in. We got x1 is equal to a times, or not a, it's our starting point. Or actually, let me just write it. I didn't write it over here, so that's why it got thrown off. But we know that's just 1 plus 1 times 0.5, which is just 1.5. From here, you can see that it's copying these values. So if you do x2, you should get 2. If you do x3, you should get 2.5. However, for 4, you can start it off, and you won't get, you don't have it here, so you have to work it out. And you actually will get the endpoint, the other endpoint. So here, notice how you got the starting point 1. And here you'll get, I shouldn't say endpoint too much. I feel like the difference of endpoint is going to be confusing. You'll get the ending of the interval here. So I'm hoping that distinction is not necessarily automatic. It's not something you're supposed to come to the conclusion of, but it's a fun pattern to notice. So for 1, it will appear when you use the left endpoints, and then for 3, they'll be used when you get the right endpoints. Same thing could be seen visually here. 0 is used right here. So it's used for that interval. And then 8 is used right here. So eventually you're going to plug in f of 8 and f of 0 respectively. Then, similar process to get the area, you simply just, well, for these 4 entries, here, if I write the 4 here as well, you add up all of these heights and then times the width of x, the differences of x that you're adding to our intervals. For here though, again we have the luxury of copying and pasting. So f of x1 is 3, f of x2 is 6, and f of x3 is 10. But now you need f of x4, which we said that x4 was 3. So you need f of 3. So we have 2 times 3 squared minus 3, which that guy is going to be 18, and then minus 3, and you're left with 15. So now let's go ahead and actually do the value. We got, let's start off with 3 times 0.5 plus 6 times 0.5 plus 10 times 0.5. Oh, excuse me, I realized the decimal. And plus 15 times 0.5. And again, you can just type up this whole expression into a calculator, and you should be able to get an answer. So 3 times 0.5 plus 6 times 0.5 plus 10 times 0.5 and plus 15 times 0.5. And I get the number 17. So that means that the true area, because of the under and overestimation logic, that means that the area is somewhere in between 10 and 17, the true area. These are approximations which have their own validity, technically, but if we're going to be technical about that, then we have to include the fact that while these are valid answers, the true area is just in between these. And we say in between, we say this is less and this is more because using the left endpoint provides us with the underestimation. Using a right endpoint provides us with an overestimation. This process of approximating area under a function using rectangles is called the Riemann sums. The more rectangles we use, the better approximation will be. So, if we were to take an infinite number of rectangles, so that means if we take the sum as many rectangles as we possibly can to infinity, then that area will exactly equal the sum. But how do we get this? Using integration, which we'll talk about in the next video. So your day 1 does not have a worksheet, which is only because the worksheet combines 4.1 and 4.2. And it's a bit layered, so I can't just do the thing like I've done before where I give you, let's do half of it. They're kind of layered to stack on top of each other. So just for today, we won't have a worksheet. But still make sure there's still going to be a homework posted, and obviously still make sure you're keeping up to tabs with everything else. Alright, that's it guys. I'm going to see you all in the next video. Bye-bye.